Hello everyone. Today we are going to learn about conductors and insulators. Conductors are those materials through which current can flow easily, like this we have studied in lower classes. Now they can conduct electric current because they have free electrons with them. In conductors, when we apply an external electric field, suppose this is your conductor, we are applying an external electric field E0, say in this direction from left to right. Then the free electrons, they rearrange themselves in the conductor this way and produces an internal field. Let us write it as EIN, internal field. And the direction, the magnitude of internal field will be in this direction from positive to negative, and this is the applied electric field. It is E0. The two electric fields, that are applied one and the internal electric field, will give rise to an electric field intensity inside the conductor as 0, as both their magnitudes are equal. This arrowhead lengths, you can see the magnitudes are equal. That will happen in case of conductor. In conductor, the resultant electric field intensity E is equal to the sum total of the applied electric field intensity plus the internal electric field intensity produced inside the conductor. This is your vector notation. But when you write down its magnitude, then E0 minus, this will become E inside. This is external, this is internal electric field. Then the sum total will come out as 0, as both the magnitudes are equal. That will happen inside the conductor. This property, we use it as some instruments to keep it safe, not to get influenced by external electric field. If you take a hollow metallic conductor like this, and then the instrument that you want to keep protected, if you keep it inside, then the charges will be outside the conductor, and inside there will be no charge. So here the electric field will be 0 inside, and this instrument will remain protected from external field. This process, we call it as electrostatic shielding. We call it as electrostatic shielding also. So this is in case of conductors. Now let us see insulators. Now some examples of conductors, if I say, all of you know all the metals are good conductors of, almost all the metals are good conductors of electricity, silver being the best. Now when you talk about insulators, the other name of insulator is dielectric. These are the materials through which current cannot flow. Example, dry wood, paper, rubber, plastic. These are the substances. Mica, they come under these insulators. They are also known as, in this class we will be studying it as dielectric. In case of dielectrics, they don't have any free charges with them. All their charges are bound charges. Bound charges, if I say, if I take a rectangular dielectric like this, the charges are forming like this. They are bound to each other, one negative charge with one positive charge, another, suppose here positive charge, then here negative charge, then here suppose positive, then here negative, then here positive, here positive, then here negative, then here positive. Like this, they are all bound to each other. They don't have any free electrons with them in dielectrics. But once we apply external electric field to these bound charges, they rearrange themselves like this. All the negative charges, they will come one side, like this. And all the positive charges will be on the other end, that is the right hand side. Like this they will rearrange themselves once you apply electric field. This is without the application of electric field. It will look like this in normal condition. Once you apply electric field from outside, then they will rearrange like this. So this one we draw somewhat this way. This side we draw negative and right side we draw positive, because right side all you can see it is positive, positive, positive. So here if this is the dielectric, we are applying an external field E0, then in this direction from left to right. Then the negative charges we draw this way, and this side will be positive charges. But unlike conductors, here the magnitude of electric field, applied electric field, if it is this one, then the inside electric field the magnitude will be less. They will produce dipole, and then the polarization will write as EP. The resultant electric field intensity inside an inside a dielectric will never be zero. In vector form, if we write this as E0 plus EP. But in scalar it will come out as E0 minus EP, as EP is in opposite direction, and this will never be equal to 0 in dielectric. This property we use it while making capacitors. Now after a while we will be discussing about capacitors. Capacitors are like vessels for storing charges, like as we store water inside a bucket, like that capacitor if we use, we can store charges. It has got different functions as well. In rectifiers and all, capacitors are used as filters. Now in this case, this here, the resultant electric field intensity is never equal to 0. Whereas in conductor we have seen that the resultant electric field intensity inside the conductor is 0. But if you apply this external field, more external field if you apply to a dielectric, then from these bound charges, these electrons may get detached from the dipole, and then they may come out. In that case, the electrons will become free electrons. So like in conductor, they have free electrons. That's why the net electric field intensity is 0 inside a conductor. In the same way, here also if these electrons will get detached from the dipole, and if it comes out, then it will behave, the dielectric will behave like a conductor. In that case, the phenomena will be called as dielectric breakdown. We will call it as dielectric breakdown. If the applied electric field becomes very high, then when the electron gets detached out from the dielectric, then it will become like a conductor. The electric will become or act like a conductor. Now let us know about dielectric constant. K. Dielectric constant K, it is defined as the ratio between this applied electric field E0 to the resultant electric field, or the reduced value of electric field inside the dielectric. For vacuum, as we know that in vacuum there is no polarization, because in vacuum there is no charge, nothing is available. This value of E0 and E both are equal. So in that case, the value of dielectric constant is 1 in vacuum, since applied electric field will be equal to the electric field, the resultant electric field. This term will not exist. EP will not exist. This EP will not exist. Then E will be equal to E0. In such a case, the value of K, the dielectric constant, will be 1. Here, yes, it is in scalar form. So it should look like this. Now the next topic that we are going to discuss is capacitors. Or capacitor. A capacitor is a system of two conductors. Suppose this is one conducting plate and the other one like this. Two conductors or two conducting plates separated by a small distance, and in between there should be an insulating medium. If there is an insulating medium in between, one of the plate suppose is given a charge plus Q and the other plate is given a charge minus Q. The potential in the first plate, that is the positive plate, that it will be plus V, and the second plate, that will be minus V. This system of arrangement of two conductors near to each other, we call it as a capacitor. Here this positive charge which the plate possesses, we call it as the positive plate, and the negative charge which the plate possesses, we call it as negative plate of the capacitor. Here for every capacitor it is found out that Q is directly proportional to the potential difference between the two plates. Now this potential difference, when I say V, the charge that is present in the positive plate, the potential is V plus. Suppose you can write like this also, and V minus can be present like this. The difference between these two potential, V plus and V minus, we call it as the potential difference between the two plates, that we are writing it as V here. To remove the proportional sign, we use a constant term called capacitance. We write it as C and this is V. So capacitance C is equal to charge per unit potential difference. The capacitance of a capacitor. Now when I say capacitance, the capability of holding charge in the system or in a capacitor will be given by the charge Q divided by potential V. The unit of SI unit of capacitance is farad. SI unit of capacitance is farad, and 1 farad, when you say, is 1 coulomb of charge. 1 coulomb of charge, when the potential difference between the two plates is 1 volt, then the capacitance will be called as 1 farad. Now let us see how to calculate capacitance in a parallel plate capacitor. Suppose you have two parallel plates. Let us mark it as X and Y. One is given positive charge and the other one negative charge. The distance of separation between the plate, say it is D. The positive charge is insulated, whereas the negative charge, this is earthed to the ground. Let the area of the surface that is facing towards each other, let this area be A. Let the area between the two plates be A. Then the electric field intensity inside the capacitor in between the plates can be expressed as E is equal to surface charge density of the charges. These are the surface charge densities, one for positive plate, one for negative plate. Surface charge density divided by 2 epsilon naught. We did this in the application of Gauss law or Gauss's theorem. This is for one plate. Then for the second plate, surface charge density divided by 2 epsilon naught. So ultimately, if you take LCM and rearrange, you get sigma divided by epsilon naught. Now sigma is surface charge density, as we know. Surface charge density is equal to charge per unit area. So it will be Q divided by epsilon naught into A, since sigma is equal to charge per unit area. So this is the electric field intensity in between the two plates of the capacitor. Now if V is the potential difference between the plates, two plates, if V is the potential difference between the two plates, then electric field intensity is given by E is equal to V divided by distance of separation between the plate is D, V by D. This is coming from electric field intensity, relation between electric field intensity and potential that we have derived earlier. We are not taking this negative sign we are not taking it. Electric field is equal to potential divided by distance. Electric field is equal to potential divided by distance. Now here D is the distance of separation between the two plates. So V is equal to ED. So if you put the value of E, that is Q divided by epsilon naught A, in this expression, then you get the value of V, the potential. This is equation number 1. Putting the value of E in equation 1, V is equal to, your E value is Q divided by epsilon naught A into D. And after finding out the potential difference between the two plates, you can find out the capacitance in the capacitor. C. Capacitance C is charged by potential so here charge Q divided by potential is QD divided by epsilon naught A. So this will be Q into epsilon naught A divided by QD. This one will reverse it. Then QQ, if you cancel it out, epsilon naught A divided by D. This will give us the capacitance in a parallel plate capacitor. It is clear from this formula that in order to get very high capacitance, the area of the plate, as it is directly proportional, the area of the plate should be large. Large plates you have to take it. This is the first thing. A should be large, and the second thing that you have to know is the distance of separation must be very, very small, as it is inversely proportional. D must be small. Distance of separation must be small in order to obtain high capacitance. These two things you have to keep in mind. The area should be large between the plates. The area when we are talking about, if this is the plate, then this is the area which is facing each other. The area must be large and the distance of separation between the plate must be as small as possible. Now let us discuss about the capacitance of a parallel plate capacitor if a dielectric is introduced. This topic we have discussed about the capacitance, how to calculate it, of a parallel plate capacitor when kept in vacuum, because here you can see everywhere we are using this permittivity of free space, that is epsilon naught. Now let us discuss about effect of dielectric on parallel plate capacitor. This is a parallel plate capacitor, and a dielectric with dielectric constant K is inserted between the two plates. This is your positive plate and this is your negative plate, and you are applying an external field E naught. Now the electric field intensity inside a dielectric in between the plate will be given by E naught is equal to sigma divided by epsilon naught, and sigma is equal to charge per unit area, so we can write this as Q divided by epsilon naught A, since here sigma is equal to charge per unit area. Now we know that by the definition of dielectric constant, dielectric constant K is defined as electric field inside to the reduced value of electric field inside the dielectric. The reduced value is E, the resultant internal intensity of the dielectric inside the capacitor. So from here we can get the expression for E naught. We can get it as E is equal to epsilon E naught divided by K, and E naught value, if you put it here, it is Q divided by epsilon naught A into K. Like this you can find out the resultant electric field intensity inside the capacitor, that is in the dielectric, that is placed inside the capacitor. Now if V is the potential difference between the two plates, then electric field intensity E is given by E is equal to V divided by the distance of separation between the plate. Here D is the distance of separation between the plates. So from here, if you put the value of E, or we can say it as V is equal to ED. And after that you can put the value of E. That is the equation number 1. Putting the value of E in equation 1, V is equal to E value is Q divided by epsilon naught A into K, then this is D. You can find out the capacitance of the capacitor when the dielectric is inserted. The capacitance C can be written as charge per unit potential difference. This is Q divided by V is QD divided by epsilon naught AK. So here this will turn into Q into epsilon naught AK divided by Q into D, then we cancel. So K epsilon naught A times divided by D. This will give us the capacitance of a parallel plate capacitor when the electric constant K is introduced between the two plates. Thank you and have a nice day.